Hello, my name is Baraka Holy. We are Team 19051, sponsored by HF Cores. HF Cores is a company that mass produces ceramic dinnerware. Our project was to create a mechanical arm that would work together with a rotating table to smooth and finish the rough edges of each individual ceramic piece before it is fired. The mechanical arm, known as the ceramic edge finishing device, or the CEFD, must be able to smooth the different shapes and sizes of each ceramic piece, including, but not limited to, round and square pieces. The CEFD is also required to execute these actions automatically upon being adjusted to fit the given ceramic piece's parameters within a reasonable time frame. The main objective of the ceramic edge finishing device is to be an improved version of an existing finishing mechanism that will meet the customer's requirements. The mechanical arm will be pressure sensitive so that it does not deform the clay, but is still able to adjust to dishes of any size or shape in order to increase efficiency in the product line. The system is required to move excess clay faster than the current method. Our design must be automatic, must contain easily replaceable parts, must be cost effective, and must handle non-circular ceramic pieces.
Hi, my name is Curtis Reedy. I will briefly discuss our approach to the problem and how we arrived at our final design. Our initial concept stemmed from a cam and follower rod assembly, where in our condition, the cam is the rotating plate and the follower rod is the sponge assembly tracking the edge of the plate. The sponge assembly will be mounted on a small 6061 aluminum I-beam. Deflection analysis on the I-beam proved our selection was mechanically sound while remaining relatively light. A linear potentiometer will collect voltage data as a function of displacement and relay that to an Arduino. The Arduino will collect this data and engage a stepper motor at a discrete programmed RPM. Our time analysis spreadsheet and potentiometer tests greatly aided in this process. The stepper motor will drive the arm forward or backward through the linear actuator, a rack and pinion. The gearing analysis aided in the programming of discrete RPMs in the Arduino. Upon completion of the design of the CEFD, our team realized how important analyses are to the design process.
Hi, my name is Casey Cochran. The CEFD is designed to move linearly forward and backward, following a horizontal trend as it tracks the rotating motion of the given ceramic piece. The CEFD has a motor attached to the front end of its arm that rotates a sponge, and this sponge is what is in direct contact with the ceramic piece, acting as a soft finishing surface. So our system must be able to withstand the weight of the sponge motor configuration. In order to ensure our mechanism operates properly with the additional weight, finishes within a reasonable time frame, and has a strong enough motor to move our mechanical arm, we analyzed the different components of our system. A total force analysis was done to find the max deflection of the I-beam, and a time analysis was done to show exactly how long it would take the probe to finish each side of the ceramic piece. After many considerations, we decided to use a stepper motor to run the CEFD. A stepper motor provided the appropriate torque needed to quickly change directions of linear motion while still maintaining the speed needed to match the tracking of the rotating ceramic piece. For the gear that connects our motor to our mechanical arm and would actually drive the arm, we chose a rack and helical pinion gear to eliminate any backlash and make precise linear movements. This seemed to be the best fit for our system. Using a voltage supply in a digital multimeter, we took the voltage readings from the potentiometer at 28 different positions. Plotting the output voltage against the displacement distance, we were able to use linear regression to determine an equation for output voltage as a function of displacement distance. This was all very essential in the coding of our Arduino.
Hello, my name is Eric Hamer. Some of our major system requirements were to be tested at the completed system level. Since we were unable to fully assemble this device, we had to rely on our analysis for those requirements. The most important requirement was that the device was precise enough that it would not damage the ceramics. Unfortunately, we were unable to ensure our device was capable of this requirement. Other incomplete requirements include being an automatic system, being able to work in the current environmentals of the factory, foreign object mitigation, and safety housings. We were able to incorporate the rest of our requirements. This video is the heart of the electrical assembly that we were able to accomplish with this project. for our own sanity, we wanted to be able to plug into any outlet. For this purpose, we obtained an AC to DC converter. Power is fed from the wall to the emergency shutoff switch. And then fed into the motor. The Arduino accepts 2 potentiometer readings in succession and calculates whether the motor should move forwards or backwards.
Hello, my name is Anthony Collett. The team had experienced many surprises throughout the design of the CEFD. The first problem that occurred was the linear velocity of the arm. We initially planned on driving the arm with a DC motor with one velocity. This would move towards and away from the plate that was to be finished. We quickly realized by dynamic analysis that we needed a varying velocity to maintain constant contact with the plate. This means that we had to change the way we thought about the motor. Initially, none of us knew very much about motors. Our mentor and sponsor had mentioned that a stepper motor may be useful in this situation. After a lot of resources, dead ends, and many people not knowing the information we needed, we finally found someone who knew. A hero by the name of David Stinky was able to help us match a motor to our requirements. Since we were now using a stepper motor, we had to rethink our electrical plan. We had planned on using an integrated circuit, but this wouldn't work with the stepper motor. We needed to use an integrated driver and control it with a microcontroller. This is where Curtis and Eric had taken the time to learn about pulse width modulation. This would allow the potentiometer to give positional data to the microcontroller, which would activate the motor at discrete linear velocities. Overcoming these issues demonstrated to the team how important analysis is in the design process. The biggest surprise of all was COVID-19. We did not foresee this project coming to a full stop so quickly.
Recommendations. If we were to begin this project again, or if another team were to attempt to solve this engineering problem from scratch, we would have some recommendations. The first is to consider a ball screw actuator. They offer extremely low friction and high precision. With some models, the sponge assembly could be mounted right onto the actuator housing. The second recommendation is to begin analyses and models immediately. They are invaluable to the design process. The final recommendation is not to be afraid to make changes. Throughout the design process of the CEFD, we made many changes to overcome issues brought forth by our analyses.